Lake Tahoe's aquatic food web has an interesting history, as it's been altered by species introductions over the last 200 years. In a lake ecosystem, many plants, animals, and microbes are connected through the exchange of nutrients and energy of a food web. Each species has a special place within a food web. Primary producers, organisms such as algae, are the foundation of every food web. They utilize energy from the sun, or photosynthesis, to produce biomass from carbon dioxide dissolved in the water. Algae is then eaten by primary consumers, the tiny zooplankton in the lake. Secondary consumers, larger zooplankton, or small fish, consume those zooplankton. A similar process continues up the food chain to larger organisms, ending with top predators such as osprey, bears, and humans. The process yields waste along the way. Microbes serve an important role, effectively decomposing and recycling organic matter back into carbon dioxide and nutrients. Fisheries biologist Brandt has been studying Lake Tahoe's food web for over 30 years.
Historically, Lake Tahoe's food web was very simple, but it became more complex over time due to species introductions. Back in the 18th and 19th centuries, Lake Tahoe had a highly productive fishery, and as much as 100,000 pounds of cutthroat trout were harvested from Lake Tahoe in a single year. Lake Tahoe could produce so many large fish because the energy flow in the food web was very simple and very direct.
In subsequent years, rainbow trout, brown trout, and kokanee salmon were introduced. But it was the introduction of the mackinaw, or lake trout, combined with overfishing that resulted in the demise of the native trout. By the late 1930s, they had all been eliminated from Lake Tahoe. Arguably, the most harmful introduction to Lake Tahoe was the mysis shrimp in the 1960s. Let's join Captain Brandt to learn more.
We go out on the lake at night to catch mysis shrimp. Mysis do a daily migration. They swim down to the deep, dark depths of the lake during the daytime and then swim back to the surface after dark. So we go out at night to collect them when they're near the surface. The mysis introduction was intended to supplement the diet of fish, but it failed for two reasons. First, since trout and salmon are sight feeders, they have a difficult time seeing and feeding on mysis. Because the mysis are not available to the fish as food, the fish have actually decreased in size since their introduction. The second problem has to do with the diet of the mysis themselves. From the time the mysis shrimp were first introduced, they almost totally consumed an important part of Lake Tahoe's zooplankton community, the cladocerans. These zooplankton species, Daphnia and Bosmina, are important because they ingest huge amounts of algae and fine sediment particles that are washed in from the watershed.
It is these tiniest particles that control clarity in the lake. At the same time Lake Tahoe was experiencing a loss of clarity due to uncontrolled development, it was also losing the natural lake cleaning power of Daphnia and Bosmina. But there may be some good news on the horizon. TERC researchers and their partners have been experimenting with ways to efficiently remove mysis from the lake. If the research pans out, the Daphnia will once again become part of the restoration of both lake clarity and a healthy Tahoe food web. We should all be very careful that we don't introduce foreign organisms into the lake because they can have unintended consequences. That's actually an important lesson for all ecosystems. Take a look at the posters to compare the historic food web to the current food web of Lake Tahoe. Can you count the number of introduced species?